world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance.
Welcome, lads and ladettes, to Aether Roundtable 115, Snail's Law and the History of Astronomical Refraction.
Did you say Snail or Snail?
Ooh, you take a guess.
All right, so today's presentation is going to be on Snell's Law, not to be confused with Snail's Law, but this is the Snell's Law invariant, which basically is a good way to show that the way you're calculating refraction is true, kind of like conservation laws. If you can show that your angles are invariant, then you're in good agreement with the established laws of physics for how light propagates through a medium. And we'll touch on that as we continue, but this is to provide a history. We're going to take a look at the history of astronomical refraction, because before we get into the main prezi here, we're going to take a look at this. Oops, that's the megabonk. That's not what we're going to look at. We're going to take a look at this. This is stellarium. If you go into stellarium and you pick a star and you set it to your zenith at 90 degrees and you take a angle to the horizon, or every 10 degrees of elevation, and you note the refraction difference, you'll see that as the stars get closer to the horizon, the separation from their true position and their apparent position becomes larger. So here at 60 degrees, there's only a reported 34 arc seconds of difference between the true position, meaning like the light source, versus the apparent position or the refracted position that we do see. Almost indistinguishable in position. 34 arc seconds is very small. So as we continue here, we're at 50. We come down to 54 arc seconds, so almost an arc minute. That's getting to significancy, but still not very much in terms of a difference, just raw looking at it. Now we have, as we continue down to 40, we hit the 1 arc minute mark. Down to 30, we're almost at 2 arc minutes. And at 20 degrees, we get to 2 arc minutes, almost 3 there. And then 10 starts to ramping up here. So we got 5 arc minutes. At 5 degrees, we have 9 arc minutes. 2 degrees, we have 16 arc minutes. 1 degree, we have 21 arc minutes, almost 23 there. Or no, sorry, that's only 21, closer to 21. And then they have calculations for things below the geometric horizon, meaning under the Earth relative to the observer due to the curvature. And, no one has proposed any experiment to ever measure that. The closest someone's ever done to try and show that an image refracts up over an object after it's been geometrically occluded was our boy Vanby, and he did not get the image to lift up once it's actually geometrically under something. He couldn't do it. But nevertheless, they see the star, and time-wise, because angle equals time, and the star's constantly moving, they can calculate when it should hit their geometric horizon. And because they still see it, they need an explanation for it. So thus they invoke the astronomical refraction difference. So as their timeline goes on and the star remains visible when its true position is now 5 degrees below, or at 0 degrees at the horizon, they have 28 arc minutes of refraction. So almost half a degree to explain why the star is still visible. And then when the true position is at minus 5 arc minutes, they go up to 29 arc minutes of refraction. Minus 10, they come up with 30 arc minutes of refraction. Minus 20, come up with 31. And negative 30 is 33 minutes of arc there. Now let's convert that into time real quick and see how long it takes for something to set when it's 33 arc minutes of refraction. So, or 33 minutes, sorry. So about an extra 2 minutes. So when they talk about the sunset and how it's already set and we're looking at the after refracted image and all that, how they came up with that timing difference is, basically a curve fit through model computation. And we're going to get into exactly that. Yesterday during the Celtheo Prezi, when I was kind of touching on this, Shane pointed out that as you get closer, as your zenith distance gets closer to the horizon, these numbers start to really spike up. And why do they do that? Well, there's a specific mathematical framework that's causing that sort of divergence, and we're going to look at how they deal with that, how they computate it, and why it's necessary. So starting off with the highest level a primary source that we could get, we have the explanatory supplement to the Astronomical Ephemeris and the American Ephemeris and a Nautical Almanac. Lots of ands and thes in there. But basically, this was a book put together with the purpose of explaining to people the history of how they came up with the almanac and the corrections therein. Now, they don't touch on refraction in this book. This book is explicitly about the true positions of the stars and how that relates to the coordinate system, because the true position of the star is what defines the geographic position on the ground. So you might have heard that for every place on the so-called globe, there's a star that has a corresponding geographic position, meaning that if you were an observer standing at that location looking up at 90 degrees, you would see that star at your zenith. And they use this model to assert, that the Earth is a globe, etc. But anyway, this book is about all of their corrections, how they tabulate everything, how the whole backbone of it works. Now, in here, they mention the difference between topocentric and geocentric positions. Now, these are really useful terms because celestial navigation and the use of the coordinate system is dependent on transformations to a fictitious location to bind that geographic position of the star to 15 degrees per hour, 60 nautical miles per degree. Without that, the geographic position has no physical meaning in reality. So they go on to make the distinction here between the apparent place of a star. The apparent place of a star is the geocentric position, and there's even a book called The Apparent Place of Stars, and it goes into detail about all of that. Now that sounds like like double contradictory or whatever, because they have the geocentric position and they have the apparent position, and then they're calling the apparent place of a star a geocentric position. There's a little word terminology cluster there, but to keep them separate, apparent place is different from just apparent. So kind of keep that in mind when you're if you were to go through and read this or something, to not get confused. But anyway, so here they're saying that there's corrections that they make. An observed position is therefore directly comparable with the apparent place after corrections. So you make your observation and then you subtract out all the instrumental errors and also refraction, if appropriate, at the angles, and any diurnal aberration, just basically anything that needs to be subtracted out to find out where that true position would actually be. You account for all that. So that's how all that works. So in here, they also make a note about how they're not going to touch on accounting for refraction in this book in particular, because that would be a whole separate subject that would, add many more pages to this already very large book. But they give some citations here to follow up on if you're interested in learning about the refraction model and how it's used. So here we have textbooks that give the basic theory of refraction and corrections. So this Chavant and Smart here, two awesome textbooks for celestial navigation and learning about that. So these books are basically telling you what about refraction and then how the corrections apply. They don't really go into the theory of how the corrections were calculated, but they go into some detail. So we're going to go over all of these primary sources here, starting from Chavant to Garfinkel. Sorry. We're going to go down to here, and we're going to examine what these are all about. Now, here in the theoretical discussion of the calculations of refraction, this is where we're going to get into the gravy. This is where the backbone of the model comes in from. This is where you take your real world empirical data, you throw it in these formula, and out comes the globe. Well, that's interesting. So how does that work? Well, we're going to get into how they calculate everything on the back end of it. Okay. So let's see here. So we already went over the geocentric and topocentric position. So topocentric is observer. That's where you're standing and looking, making the observation. The geocentric position would be where you do the transformation to remove refraction. That would be the comparison. And then, of course, all the positions of the stars for the true positions is all done with respect to the with respect to their zenith position on the night of the vernal equinox. This is otherwise called the first cusp of Aries or the first point of Aries. So it's relevant in how it ties it all together to that geocentric position. And then you're going to view it from the topocentric. And then you're going to take out your corrections, your optical corrections, instrumental air and stuff. And then you're going to get that nice Aries position that's going to define that geographic position for you. Let's see. So more on that. This is just kind of re-illustrating the same thing. The apparent position is derived from the geometric position by application of corrections for aberration, where they are relevant for refraction. So again, that's just kind of illustrating that the geometric position comes first in order of things, or you're deducing the geometric position because that's the backbone of what you need to get to find usefulness in the coordinate system. So I was looking through a celestial navigation manual by a gentleman named Umland, and he gave some really nice, clear explanations to everything. And he had this nice table for refraction angles for the elevation bands going from 90 all the way to 0 here. And he gives the refraction corrections for them, which we looked over earlier in Stellarium. I went in to verify them. They're all pretty much exactly as he says here. Or at least very close enough to, I don't care about the difference. So here would be your tropocentric position. You're seeing the apparent position, and you need to do math corrections to deduce the true position here. Well, based on the angle that you're looking at here, at minimum, they say you're going to be dealing with this much refraction. So if you're in the 40 to 80 angle band, if you're doing cell nav with an 80-degree angle for some reason, this is the refraction that you're going to be dealing with. Now, as you get lower here, we have these numbers. So we're curious about how they came to arrive at these. This is, so he kind of touches on it a little bit, saying that they're empirically derived, which just means that they're derived from basically model fitting. And we'll get into exactly what that means as we continue. So to start off with the first citation from the supplement to the Ephemeris, we have Chavant's Spherical and Practical Astronomy Manual. And in here, we found a really interesting thing about occlusions. So you know how we use occlusions for the celestial theodolite? Well, you can use occlusions to determine the difference between local solar time and sidereal time. So back in the day, clocks weren't easily synchronized. You had to get your local solar noon time, and then you had to deduce what sidereal time would be with respect to that. So the way that they would do it is they would take any terrestrial feature. And what I was reading, they were using buildings and stuff, but they mentioned that you could do things off at the horizon. So really anything, a building, a mountain, as long as you know the elevation, so you can get the angle. When you get the occlusion, you get the time. And when you get that angle and time relationship, you know, you can mark the difference between your local solar noon time after you get two occlusions. So you take 2 star occlusions, subtract the difference, subtract that difference from your local solar noon, and now you're on sidereal time. But he makes a special point here that says several altitudes or zenith distances. So a zenith distance, real quick, because we're going to be using that word a lot. A zenith distance is if you were looking up at your zenith and then you were counting the angles as you were going down. So if you're at a 70-degree zenith distance, you're looking 30 degrees off of the horizon. Does that make sense? Because it's like a complementary angle to 90. So whatever the zenith distance is, so if they say 70 zenith distance, that means you're looking 30 degrees off the horizon. If they say 80, you know, you're just looking 40 degrees off or whatever. So same, or no, I'm sorry, 20 degrees, sorry. So same situation there. Nope, 10 degrees because it goes up to 90. My bad. I was thinking hundreds. Okay. So anyway, that's how the zenith distance situation works. Just basically the angle going down from the top instead of going from bottom up, from the horizon to the top. It just goes in reverse essentially. So that's how they talk about it. So anyway, he says here, for small zenith distances, the distance or the difference between the apparent position and the refracted position will be insensible, which we verified earlier. If you were using a terrestrial feature at an angle of like, you know, 80, 70, 60 degrees, that time of occlusion is going to be pretty close to the true position. So you don't really need to account for that that 1 second timing difference that it's gonna come up with, or thereabouts. But he says here, at great zenith distances, so when you're close to the horizon, actually he says when you're under 80, when the zenith distance should be computed, or at great zenith distances, we should compute several refractions, but under 80, we take the refraction r for the mean apparent zenith distance z naught and correct it as follows. Now, the mean zenith distance refraction correction is an interesting one. We'll get into that as we continue, but basically they have like a rule of thumb where if you take the tangent of the zenith distance times the local temperature, that'll give you the refraction amount. It'll give you that small arc second difference. So they take that as like, just good enough to add some refraction to it to make it like seem like they're doing a calculation. So anyway, they use that as the rule of thumb. But if you're doing larger distances than that, zenith distance wise, you need to account for refraction. And by account for refraction, he's saying you need to subtract that amount of refraction, because the subtracting that's going to tell you where the true angle of the star and with respect to that occlusion, and that's the angle that they want to determine sidereal time. So extremely important relationship there in history of using occlusions to figure out timing differences. Very similar to how we're using the celestial theodolite. So I thought that was a really interesting thing to include here that I found out of this manual. Now, in terms of use of refraction from it, I didn't find anything out of the ordinary. It's pretty standard. He's just, you apply the old refraction correction, etc. Nothing fancy. Moving on to Smart's book here, we have just basically walking us through that same relationship that we just talked about, how they do the zenith distance estimation for the constant mean refraction, where you just take the tangent of the zenith distance times the local barometric pressure or temperature, sorry, and then that'll give you the angle correction there. So super small corrections there. For many purposes, Formula 7 is sufficiently accurate for zenith distances not exceeding 45 degrees. So if you're looking at a 45 and up, you can use this mean zenith distance refraction estimation, and it's just as good as if you had actual measurements or whatever, apparently, of the refractive conditions to calculate it. So as we continue, there's going to be a key feature to understand, and it's called a secant. So this is a trig function here, and this is where a line intersects a circle, not through the center. So like the center would be, radius related, diameter, etc. This is slicing it like this. So if you could think about it like, say you're an observer here in the center, and say this is all atmosphere. Well, the angle at which this cuts through that circle of atmosphere, that's the secant. So this function is going to be used a lot in the next computations, because this is actually the backbone of how they get that scaling feature for things to scale really hard at the horizon, like why this fails at the horizon and whatnot. Because when you trig this out, as the angle increases, it gets, it just wildly diverges and doesn't make any sense. So they have to do a couple of things to rein it in and make it. They have to give it boundary conditions and stuff. So we'll get into all that. But this is an important feature here that's going to be referenced, the secant. Everything else is pretty standard. We should all be up to date on these, but we don't often secant around here. So figured I would include the diagram. Go ahead.
Well, yeah. What's the difference between the secant and the horde?
Ooh, great question. I assume that it is the like, see how the segment is within the thing. This is
it's a segment.
This is like cutting a slice through it. So I assume that's different somehow. But they look very similar. We can look that up towards the end of the Prezi though. But so real quick on refraction here in Snail's law, there's an important feature called the refraction invariant. And a refraction invariant means basically all of these angles coming in are proportional to the angle that is produced when it when it enters the medium. So that angle change relationship between like Z and Zn right here, these would be proportional. So you could trace this relationship angle wise all the way back to the source. And if in doing that, preserving that invariance is like basically the equivalent of using conservation laws to show that to show what you're doing mathematically isn't violating any known laws of physics. So if you're conserving momentum, etc., that's a good sign. So if you're able to preserve the refractive invariant, you're doing things correctly for optics. So let's see. This is just some diagrams to kind of show what they're asserting here mathematically. So you see these X, E, C, and A. You can kind of think of these as different stratified layers in the atmosphere, because that mathematically they have infinitesimal sections of this layered out. So and that's what creates this gradual bending here of this angle change. So this is a like, the diagram makes it look big, but it's a really, really small angle change over a really, really big distance. And they relate that through infinitesimal segments by stratifying the atmosphere, making it homogeneous, removing dynamic effects and all of that. But we'll get into that as we continue. But just to kind of put forward their conceptualization of how they're interpreting how starlight enters your eye at an angle on a globe, and why those angles deviate from the true position of the star, is they're saying that it has to cross through more layers of the atmosphere, which causes more refraction. So the steeper the angle you're looking at, they would assert that, well, then there has to be more refraction, right? That makes sense. So that's how it all comes out for them. Okay. Now we're going to get into their computational modeling of all of that. So in the next part of the references that was given from the supplement to the ephemeris is the one from Willis John, where the determination of astronomical refraction from physical data. Oh, from physical data, huh? That sounds promising. We're going to get an actual model here. Spoiler alert, we're not. So he starts the paper off by just kind of defining coordinate systems and all that. Nothing too fancy. He makes a couple assumptions about the atmosphere and how he needs to calculate it. So he touches on that same thing we talked about earlier. So if the curvature of Earth is neglected, astronomical refraction is equal to the refractivity of the local air multiplied by the tangent of the zenith distance. So earlier we talked about that multiplying the local air tangent to the zenith distance, giving the refractive condition. So this is how they do that. So if you're not considering, and by not considering Earth curvature there, he's talking about like, your angle is not steep enough to be looking through all that gradient of atmosphere or whatever. So you can just use that for their thing. So if the curvature is not neglected, then the refraction computation involves quantities representing the refractivity of air at all heights. Oh, all heights. That's interesting. So so part of how this computational model works is they bind the refractive qualities as a function of height above sea level, essentially, rather than actual conditions, because the way that this is all going to get smoothed out, no matter what direction you're looking, the refraction conditions are going to be the same when this all gets turned out. So the loci of refractivity are assumed to be concentric spherical surfaces. So earlier when I talked about how they have a whole stratified model that's layered out, so these would be concentric circles of stratified atmosphere going outward from the center of Earth. So they start their model at the center of Earth where, there's Earth in the way, but mathematically that's their starting point. And then after they get to the surface here, that's where they start out their model as it extends out to about 20,000 kilometers, I believe. And then like at the 10,000 kilometer mark, that's where the atmosphere starts kicking in terms of like where this light's going to start bending, because that's where they've put the limits for their gradient. That's where they've imposed their height limit. That's a boundary condition for the lads. Okay. So let's see here. See where we're at on the notes. Okay. Okay,
Did you
so
say? Did you say 20,000 meters, or what was it for the
kil-
terrestrial, the
kil-
first
kilometers. So from the
kilometers?
surface of the Earth out to 20,000 kilometers.
And that's when the atmosphere kicks in.
So at about 10 kilometers, that's when they'll start having like effects. Like the extension out
Okay,
to the
gotcha,
full 20 is like such a small gradient. There's no, nothing really happens or whatever. But as it gets into that 10-kilometer range, that's when you start to get the bending.
gotcha.
Mm-hmm. So to start us off here, he hits us with the Snell invariant. So this is going to be, he starts off laying out the framework just using pure geometry and optics. So this is just starting with the Snell invariant that we talked about earlier, how this angle over here is proportional to this angle. Psi and phi would be proportional. And then as you continue, as you continue on, all of these, Z sub n1 and Z sub n2, proportional, all proportional. So that's what that means. He just starts us off with that. And then he goes on to give us, let's see, starts to give us the concentric model, and he starts defining, second. Okay. Yeah, so basically what he's doing here is just setting up the symmetry for the coordinate, or like for how they're going to interpret the distribution of the atmosphere. And then as it continues, it's more of the same. This is describing how the local how like that ray invariant that we were talking about for Snell's law will get canceled out, and then he'll introduce a new term as a dimensionless parameter that's defined as a ratio of Earth's curvature with this, where was it? R over R naught. Is this the right one? Let's see it. Oh, yeah, up here. Yeah, so he's, basically setting the boundary conditions for what he's going to integrate here with this integral. Okay, so as we continue, now he starts describing that stratification of the atmosphere using different types of convergence, or series convergences. And again, when I was talking about how it starts to, like, as you expand this out, it starts to go out to infinity, because what they're doing here is they're building stratified layers from this. So as you expand this series out, after the boundaries and everything have been put into it, it'll diverge to infinity if the zenith distance is close to the horizon. So how do they fix that? What do they need to do there? So basically just through computating and integrating, and then anything that is anomalous, they turn that into a correction factor, and anything that's like the Novaya Zemlya effect, anything that is anomalous gets wrapped up in the corrections. It gets basically smoothed out, because the whole purpose of all of this is to be able to put in real data, but it's going to get smoothed out into the model by the boundary conditions set by how he's going to integrate everything. So it's all setting up for, we can take any meteorological data, put it into these equations, and it's going to output the globe. But that's because the boundary conditions and input conditions, started with the globe, so it should be no surprise. But basically, this is all going back to that secant. So describing that path of the ray as it's cutting through the atmosphere, that's going to be their driving force for making the refraction a function of angular altitude rather than actually a part of the parameters that they're going to put in from the meteorological data. So as they continue on with their it was this one. So as they continue on here, we notice they have an A secant, B secant now, and a C secant. So A, B, and C are now temperature, pressure, and refractivity, different variables that you can put in. And you could put like these would in theory these would represent real data point values. And this is how they expand that out and how it fits into the globe. This is how they make the atmosphere a smooth stratified gradient that is what's the word I'm looking for? Oh yeah, that's static and not dynamic. So in this scenario that's been set up, the atmosphere is static. There's no room for dynamic conditions. There's no ducting. There's no thermal inversion. None of that. Like any anomalous effect that we actually observe gets, basically, you could think of it like it gets rounded off in the math when they solve this. So it doesn't exist. These are static conditions. They're not dynamic. So if there's dynamic conditions, those are anomalies, and those will be corrected out through the smoothing of the integration here, which was all set by the boundary conditions over here, starting with none other than Earth's radius. So let's see here. So we can continue on. All right, now after all of that, he goes on to kind of justify his position as to why he's doing that. So he says that purely radiation equilibrium does not hold at the lower 8/10 of mass of the atmosphere, because a lot of how they calculate is based off of air mass. It doesn't have to do with like the temperature and pressure or anything. It has to just do with the mass of the atmosphere, so to speak. That's another part of the way that they control the computations for it and make it relevant to that instead of actual figures. But anyway, by saying how basically there's like a thermal equilibrium, he's justifying that for his stratified static atmosphere. Then he goes on to talk about how he's going to input this real world data here. And he starts doing that. And as he starts solving those out, what do you know? He builds an atmosphere that describes the globe, that puts the positions that would put the apparent positions of the stars exactly with the exact amount of refraction that was calculated earlier, that we looked at when we went into Stellarium and saw those angle changes, when we looked at the Umland guide and he had the refraction per 10 elevation band of angle. Same scenario. This is where it all comes from. And the extremely important part that he says here is that it is not strictly correct to say that the practical coefficient of secant z, which is the cutting that line to the zenith distance, term in astronomical refraction, is independent of the law to be adopted for the distribution of material in the atmosphere. So earlier when I was talking about how it's all based off of air density and all of that to set the conditions, well, here he's just like, the refraction correction depends on how much atmosphere you assume there is for there to be distributed among it. So you set the conditions, you get the output that you desire. So all freedom is gone at this point in terms of like, I'm going to put data in here and see what comes out of it. This is going to fit all data to this model. Everything's going to be averaged, truncated, symmetrized, and reduced into constants. So when you reduce it into a constant, that's how you basically make it irrelevant. And then you can also, the constants that they use are all changeable. How could the constant be changeable if it's constant? Well, it's changeable because of the way that the boundary conditions work with how they're integrating it. And it keeps it so that basically anything you put into this, it's going to smooth it out. It doesn't matter. So this is purely an angle correction right here with the secant squared times the zenith distance. This is all the driving backbone is the angular separation and the height of the atmosphere is what we're left with. So anything we put in here is going to come out globe. This entirely depends on how much atmosphere you decide that you need. Now at the end he says the writer believes, because a lot of this some of it was when he was talking about the thermal equilibrium earlier, let's see, he was talking about dry air somewhere in here. Let's see, temperature nearly constant above zero. Where's the dry air section? Somewhere in here. Definite existence. Oh, yeah. The definite evidence exists that dry air is of a uniform chemical composition up to heights greater than 20 kilometers a second. It is probable that no substitutional air for refractivity calculations result from adopting this competition or composition as uniform throughout. So he takes this dry air as the like backbone for the stratified atmosphere to go through, and then he says here at the end, the writer believes that the direct measurement in the laboratory of the refractive power of air would furnish a more accurate value for the coefficient of the tangent z, which is that just taking that tangent of your local temperature to your zenith distance to get the correction for astronomical work that can be derived for comparison of circumpolar star observations. So what they would do, I think I read about this earlier today, but basically they would make an observation of circumpolar stars, and then they would have a wire cutting through the center of their telescope. And when the star would intersect with the wire, they would try and deduce like refraction differences based off of that. I'm not really sure how all that works out here, but basically all they did to determine how much refraction there is just by looking at the star. So there's not a lot to go on. So he's saying we could verify how that what the refractive power of dry air is in the lab and see how that compares to our coefficients. And does anyone think that they've done that? Show of hands. Anyone? They haven't. They forgot. All right. Now we get to our boy Garfunkel. Now this paper was super math heavy. This guy says that he is dissatisfied with how the previous computational models of old are basically assuming all these conditions, and they don't leave room for introducing real meteorological data. And now in modern times, when meteorological data is readily available, we need a new structure computation to integrate that so we can give the, he doesn't say this part, but so we can give the appearance of, calculating all this independently without assuming it. And he makes a quick reference to this Jay Ivory guy who is using height above, the height of the atmosphere essentially as like the driving force for his computations for how he describes refraction. And then he's actually going to build some formulas, compare, and end up with the same exact thing that this guy did using the same thing. And he's actually the way that this guy ends up doing the whole calculation, it's no different than the other guy assuming, the input and boundary conditions. But we'll take a Gandy at what this guy did to see just how different it is. So he defines all the variables he's going to use here. So we get a nice glossary of the variables. Nothing too fancy, but we have radius vector, we got temperature, pressure, gravity, constant gravity, the ideal gas law, height above the homogeneous atmosphere using the ideal gas law, et cetera, et cetera. It goes on and on. So he starts off here by giving us equation 5, which is basically setting up the ideal gas law for the, for the atmosphere, for how it's going to interact. And the ideal gas law, of course, is based on elastic collisions in a container to describe pressure and temperature and volume as a ratio. So all of these are going to be in relation to the gravitational constant that he's using. And basically, it just continues on from there. He sets up some refractivity properties, etc. Keeps going. Does the same situation where he's starting the framework for a stratified, homogeneous, medium, et cetera, that's going to be smoothed out. So let's see here. For this one, we're establishing Earth-centered symmetry. We're using basically by establishing that with the dynamic height of the atmosphere, how he was like referencing that ivory guy, what he's doing here is making it so that there's no directional gradient. So like if you're looking left or right, east, west, north, south, none of that matters. It's all going to be the same. It's removing time from the atmosphere, so there's no dynamics. It's going to be static. It's going to describe a single ray path, and there's no room again for any dynamic effects. There's no caustics, no mirages, no ducting, no inversions, nothing. This is a dead atmosphere. It's just chilling. And if you change any of those variables, the whole thing breaks, doesn't work. All right, so let's see. Equation number 10 here gets into just saying that like refraction is accumulated continuously over the integral. Each layer contributes to a small bend. We looked earlier at that diagram of the bending light ray going through all the refraction or all the stratified layers and how it had its own Snell angle to it or whatever. All of that is described in equation 10. So this is the total bending integral, you could call it. Let's see. So none of the values that are given, temperature, pressure, gravity, refractivity, none of that is evaluatable at this point. You've already selected it and it's put into the model now. It's already the values that you are setting are going to dictate how the new value, like when you put in real data, it's going to like morph into what you already started with the with mu, rho, and time and T and gravity. So temperature, pressure, volume, refractivity, and gravity. Actually, what was mu? Mu was the index of refraction. Yeah, so the refractivity. So yeah, by setting all those conditions there, the output of no matter what meteorological data you put in, it's going to come out to that. And he references this guy Randu a couple of times, and Randu has his own formula where he did the exact same thing, and this guy ends up deriving an approximation of Randau's formula, which isn't anything different than what Randau also did. So that guy, and also just basically setting how you calculate the model parameters, which is what we're looking at right here in this section. So as he continues on, he talks about Ivory's model, which is given here. And then we have model B. So there's just different, it doesn't matter how you, this is just model choice. This is just like your preference of how you want to calculate it, essentially. It doesn't matter because it's all going to come out to be the exact same thing. And what he ends up showing here, where does he say? Oh, am I out of? Am I out? Gotcha. So our choice of atmospheric model representation represents a compromise between meteorological accuracy and formal simplicity, permitting direct integration from Randau's formula. So they're all doing the exact same thing. They're all setting the input and boundary conditions and then integrating real world data to fit the model that they already started with. And they already know what the angles have to be. So check this out. We're going to go to this dude's paper and look at this. So as he was going through this, what was that one value? He talks, oops, 1 second, I need to close and reopen it. Good. Garfinkel. All right, where was that section at? Equal distance gravity. Hang on 1 second, see if I can find it. Yeah, right here. So he goes through and sets the n value here because what they end up calculating is for, what's the word I'm looking for? Centric varying corresponds. Not monotonic, it's shoot. Anyway, this value describes how it's not the n of like the typical refraction index. This is for a poly something, can't remember the word. Let's see if I can find it. Polytropic. Okay, there we go. Polytropic. So the choice of polytropic index will be justified later. So polytropic. Polytropic is the thermodynamic process that allows for the relationship between pressure, volume, and the refractive index to be treated as a constant. So anyway, he chooses that 5 value there, and then the difference between the other two values. Oops, I went past it. 1 second, because it's pivotal to the end when he for what we're going to read. Okay, so he has two different values he could choose from here: 4.8 or 5.1. He ends up choosing 5, and then the difference 0.3. This delta n, he's going to turn this into an index error, which will be turned into a correction, which when you put it back in, it basically gets smoothed out, and anything that's wrong, anything that would be wrong with this doesn't matter because it just got absorbed essentially. So when it comes back down to here to talk about where did he do the summary of that dude's model? Oh, right here. So he starts comparing what he derives to what Randau and what Pokewall derived. So these are the refraction values based off of zenith distance. And you see here, they're all in good agreement with one another. 80 degrees, spot on, 81, 82, all the way down to 90 degrees zenith distance. He has basically the same exact values that they all have. Now, did he just arrive at these miraculously because the meteorological data supports the Earth being a globe? No, of course not. He literally force-fed the globe into a structure where he could put real-world data into it, and the output would be the globe. And the fact that his equation, what was it? Equation 12, I think it was. Approximated. Yeah. So this whole setup here that we started with, that we went over earlier, is actually just that other guy's equation. Like there's no difference in what any of these people are doing. It's not a unique thing. He didn't discover anything. This is literally just math doing the same thing. So anyway, you saw that the values all give agreement with what it has to be essentially. And then even going back to what was it? Where's the Newton? Even going back to Cassini, Simpson, Ivory, and Newton. These are how they all calculated their polytropic models for the atmosphere. So basically, describing how that stratified gradient's going to work. This is what they all came up with for their amount of refraction. And you see they're all pretty close together. And then, Ivory and Newton, the more modern ones of the accepted values or whatever, it's pretty close to, 40 arc minutes is pretty close to like the 35 or so arc minutes they give to celestial bodies that are below the geometric horizon. But basically all we're looking at here is endless computation and model fitting. You couldn't put any data into this that would falsify it. It's all going to get rounded off and homogenized within the math. That's the whole purpose of all this. All these crazy symbols and all this integration, summations, all of that. It's all to make it so that whatever you put into it, the globe comes out. And that's to justify this large zenith distance discrepancy, because that's where the stars linger at the horizon as if they are moving away from you and not truly descending at a fixed rate, because the Earth is spinning out from under them, giving an elevation difference based on the curvature. If that were happening, they wouldn't have to go through all this trouble to try and figure out how to describe the low zenith distance situations, because most of what this is about is trying to come up with a way to describe, these lower angle observation bands, because the high ones, like, nobody really cares about, because it's really easy to approximate it by you don't even have to account for curvature. You can just use the local temperature times the tangent of the zenith distance. So this is to give them like a more scientific slash, we calculated it, we measured it, we're integrating real data or whatever kind of thing. But they're not doing that at all. Like the problem with this is, if you start with Earth's radius and end with Earth's radius, the output of anything you put inside of it is going to be related to Earth's radius. It's a fact. So there's no way to get out of it here. So because they've assumed the sphericity, the symmetry, all of that, that's it all comes out of that. So that's the end of that paper, and that concludes the first part of this presentation. There will be a follow-up to continue on with some more additional things. So, like, for example, Kat and Brian and I made some celestial theodolite measurements where we could see the refraction difference from the different times a year. The measurements were made 6 months apart, so we can compare those. So I have to go into Stellarium and adjust the temperature a little bit and see how that affects what they report the refraction is going to be. But if I remember correctly, the intersection differences were about the same. Let's see if I can pull it up here. So 1 to 2, basically, well, they were under here, so they didn't even make it over the peak, but 1 arc minute. And then earlier in the year, it was about, it was almost 3 arc minutes of refraction there earlier in the year. So anyway, we can go through and kind of falsify, how much refraction they're asserting. We can kind of judge the validity of it, because a big part of this refraction amount, remember, like for the example of Pikes Peak, not Pikes Peak, for the example of North Peak, the star's true position is geometrically below the curve of the horizon by 12 arc minutes, but it's being lifted up 23 arc minutes so that the observer sees it 11 arc minutes above the horizon. So as low as 11 arc minutes above the horizon, we have this star here with 23 arc minutes of refraction. So if there was no mountain here and the star was just continually setting, for as long as you could see it, that would be the amount of refraction that they say is existing there for that to lift it up. But because there's a mountain here to cut it short, they have to cut off this extra 2 minutes of refraction to just say that, it just happens to be that much, or whatever they, however they internalize it. But that breaks the Snell invariant. If there's that much refraction there, then that angle can't just be cut short. You wouldn't be able to trace it back to its original location. So that much refraction doesn't exist for the measurement. Otherwise, it would be lifted up over the mountain. It would linger on the top of the mountain until the star continues another 30 seconds below it, 30 real seconds, and then it'll vanish. But that doesn't happen. Never happens. So their hypothesis of making this atmospheric gradient and coming up with all these models to fit, real world data into it, is completely meaningless. No one's ever tested it. That guy said, it would be nice to test this in the lab, but, whatever. So any questions, comments, or concerns, lads?
Well, just off what you said, it's like the cell Theo is like finding a chink in their refraction armor, by testing that difference between the horizon and the mountain. It shows what,
Yeah.
That's interesting.
Yeah.
I did have a question though. You mentioned how they measured local temperature in those refraction in that paper, and was that the only measurement they did? Was just like the real life measurement
So
Was
so what
was it just a local temp?
yeah, so what they can do is they can take meteorological data from any night, any time or whatever, any location, and just put that into these equations, and that will give them the whole, that'll give them everything they need. It'll just build the
Wow.
whole atmosphere for them, around the globe to describe it as a function of globularity. And then to answer your question earlier, Shalom, I just looked up the difference between the chord and the segment. Here we have, so I'm sorry, it's a cant. So the chord is the segment whose endpoints lie on the circle, and then the secant where it passes through it, it intersects it.
Okay. It makes sense because the secant is more valuable in this case because it's continuing past the surface of their said
Yes, sir.
circle.
Yes,
Yeah,
sir.
and that being a line and not a segment does go infinity.
Yes.
Like that's the difference between a line and a segment. One
Yep.
keeps on going, and the other one does not. Gotcha.
Yes, sir. All right. Well, that was the Prezi. So I was talking to Jonathan last Friday about refraction and how it's all based off of a model and whatnot. And he was like, I'd like to see that. So I went through the sources again just to double extra make sure. And then I'll go ahead and send these to him and see what he thinks about it. But we just went through the backbone of how they determined the values that they say is astronomical refraction, how they came up with these deviations between true and apparent. And then if you want, let's see, I have an extended breakdown. I'll put the link in the chat here. I have a further breakdown on each of the math sections and whatnot to kind of just go over the variables and stuff. But I just kind of summarized it for the Prezi, but all of that is on here on astronomical refraction on the Obsidian database. Oh, I put it in the wrong chat. There you go. No questions in the YouTube chat I'm seeing. Everyone's getting it, I guess. All right. Well, with that, Liliana is going to give us a coffee ad, and then we're going to wrap up for the night, lads.
Hello.
Liliana,
Can you
weren't you
guys hear?
telling us the other night that the refractive properties of brushtail coffee once brewed is almost zero?
Yeah, I think so because it was refracting my hair in a funny way.
You put brushtail in your
Yeah.
hair?
Well, this is what happened. I ran out of milk for my coffee, and so I had some coconut milk. And so I thought, okay, I'll just try it with some coconut milk instead of regular milk. So I put some coconut milk in there and drank my coffee. And then the next morning, I was like, oh my God, my hair looks longer. And so I just didn't think anything of it. And then, so I continued with the coconut milk because, the can was kind of big and I had to finish it. And my hair just kept growing like 1 inch every night. And now it's all the way down, like past my knees. So if you drink brushtail coffee with coconut milk, it might make your hair grow super duper long. But that could just be a weird refraction too. I don't know.
Yeah, you heard it here first, folks. Putting brushtail in your hair will make it appear to grow longer.
Nice. Coffee, coconut milk, cream rinse.
Yep. All right, lads. We will see you on Thursday and or Friday night. I think we're going to do our reading night this week, lads. do some reading on Thursday night. And then we'll be back on Friday for the Friday Community Twitter Space hosted by Brian Sweet. Not to be confused with Brian Not So Sweet. Those are different people. And then we'll be back again on Monday for Celestial Theodolite update number 34. Not sure what we'll be doing on that one, but it'll be something. So tune into that on Monday at 8 p.m. And then Tuesday again, of course, will be Ether Roundtable 116. See you guys